Right, good afternoon, everyone. Well done for staying for the duration. This is the last but one talk, so thank you. I'm Robbie Jerrom. I'm one of the cloud native apps platform transformation specialists inside VMware, which means I talk about containers and Docker and Kubernetes and PKS and all kinds of emerging things. So we're going to talk about what's new and next now. Nick?
Nick Kenney. I'm subject matter expert for Cloud Native. I've been at VMware for 2 years now, almost. Yeah, ran a startup before that, so that's why I get to come along and do Cloud Native stuff.
All right, let's talk about some stuff.
All that ever was, all that ever is, and all that ever will be. Anyone name the quote? Carl Sagan quote. I couldn't avoid it. It's such a cool venue. So, turns out, space is pretty big. In the known observable universe, there's between 1 and 3 times 10 to the 23 stars in the known universe. It's a lot. And there's roughly, I've rounded this down, it's about 10 to the 83, 84 atoms, but it's about 10 to the 80 atoms in all of those stars, in all of the known universe. And the universe is quite old as well, as being quite big. It's, about 14 billion years, so roughly 10 to the 10 years since the dawn of the universe. If you try and work that out in seconds, so there's roughly about pi times 10 to the 7 seconds in a year. And there's obviously 10 to the 9 nanoseconds in a second. So you can do something quite interesting as a thought experiment. If you take the number of atoms in the universe, and if you think about an atom, atoms have got electrons, they have different states. What if you could use an atom as a processor and do a computation with it? If you imagine that we could turn every single atom in the universe into a processor, and we could then, it could do one processing operation per nanosecond. If you multiply the number of atoms in the universe by the number of nanoseconds since the Big Bang, you get to quite a large number, which is 10 to the 106th. Does anyone know where I might be going with this? So, there's a guy called Claude Shannon, and he had a friend he used to sit down at lunch with called Alan Turing, and they used to spend most of their lunches discussing how they could teach a computer to play chess. And he came up with something called the Shannon number, which is the number of possible different games of chess that you could have. And then he wrote a paper in 1950 called Programming a Computer for Playing Chess. So if we look at some of the numbers for that, so the number of legal moves that you can make in a chess game at each point, there's an average of 36 different possible legal moves you can make at each point in a game. And average game length is, so 80 ply, 40 moves. So white makes a move, that's 1 ply. Black makes a move, that's another ply. So half a move each time. If you multiply those together, you get 10 to the 120, which is called the Shannon number. So we go back to our universe figures. So if you imagine our atomic computer that we built, that can do one operation per atom per nanosecond for the history of the universe, if we try to use that to calculate all of those possible chess games, we would get to, we're basically 14 orders of magnitude off. So we're nowhere near even looking at every game of chess that you could play. That's called the British Museum algorithm, and that's basically brute forcing trying to play chess. You can brute force checkers. It took them 18 years, and they kind of cheated as well, but they managed to brute force that. So you just can't do it. You can't brute force chess. But what's interesting is in 1997, a computer beat a human, the best human in the world, at chess. Ever remember the Deep Blue Kasparov? So Deep Blue actually played Kasparov in 1996 and lost. And they spent some time reprogramming it, and it played him again. So this is you can see it's the rematch, 97, and it won. And it played him a third time, and it won again. And at that point, people went, well, 2 out of 3, let's call it. Chess is solved. We've basically worked out how to beat computers at it. What's quite interesting is if we have a look at how it actually did it. It's actually fairly basic and understandable how it played chess. there were three things. So it had a dictionary of moves, of opening moves, and this was just from books of human games that have been played. It had a dictionary of endgame states, again, just a dictionary of moves, and it had a tree search algorithm, a thing called Minimax with alpha-beta pruning, which looks like this. So the way it works, the way Minimax works is you basically say, well, okay, let's say I'm white, so I get to play first. I'll be the maximizing player. Robbie might be playing black, so he would be the minimizing player. My job as the maximizing player is to keep the score number as high as possible. His job is to make it as low as possible. So your score is based on things like the board position. So if I were to take one of his pieces, I get a high number. If he took one of my pieces, it's a low number. If I put one of his pieces in jeopardy, that's a high number. And based on, if it's a really good piece, like a queen rather than a pawn, it's a higher number. And so you have this scoring mechanism. And then you just basically have this tree of possible things. So we said there were 36 bits. That's called the branching factor. So it wouldn't all fit on here, so it's a little bit narrower. But you can imagine it branches 36 times every time. And a typical game would go for 80 of these rows. So that's kind of what you're doing to play a chess game. And what happens is, so let's start at let's see if this works. If we start at 5, up here. So if we start off there, I've made a move. It's now the minimizing player's move. So Robbie's got the choice of a 5 or an 8. And because he's got to keep the number as small as possible, he's probably going to go for the 5. Then I don't have a choice. I'm 5, and then he's 5, and that's that particular bit of the tree. Now, in order to beat a grandmaster, grandmasters will think ahead for all of their moves. And they can think roughly 16 moves ahead. So in order to beat grandmaster, you need to think more than 16 moves. Problem is, you're under the clock. You've got a chess clock, and you have a limited amount of time to do that. So you basically you think this is branching by 36 every time. We've got to go 16 in depth. This is quite hard to do. So they had a computer the size of a fridge, and even still, they couldn't get deep enough. So the alpha-beta pruning bit is these red bits. So it basically says, well, if Robbie's got the choice of 8 and 5, why would he ever choose 8? He probably wouldn't. So we can just ignore everything that's beneath that. And you can prune bits of the tree off. And by doing that, you can get down to a depth of more than 16. And that's how it worked. It's completely static. You have to understand chess to program this. And this is what they built. And it won 2 out of 3 games. And they kind of went, great, chess is fixed. Fast forward 20 years, and a computer beat a human at Go. So Lee Sedol was beaten by AlphaGo in 2015. What's really interesting here is Go is a lot more difficult. So first of all, the scoring mechanism. Who looks like they're winning, black or white? Anyone have an idea? It's very difficult to score Go. The second issue is the branching factor. So we had 36 for chess. It's 250, because you can put pieces anywhere you want on this whole board. So it was really, really difficult to do. What's really interesting is not how AlphaGo beat Lee. What's super interesting is the follow-up to that, a thing called AlphaGo Zero, and I'm going to talk about how that works briefly. I'm not going to go through all of this. I'm going to simplify it a little bit, but on the right-hand side, we've got another tree-walking algorithm. So we have something called the Monte Carlo method. And the way that works, rather than trying to look at every single branch on a tree, it just picks a few randomly. So, but it plays them. It will basically say, okay, let's say I did this, and it will pick another move randomly, then another move randomly, and it will keep randomly picking moves until the game finishes and someone wins. And it will do that a few times, and then for each of the possible moves it's got, it might be, well, okay, starting here, there's like 1 million games that could follow on from it. I've just looked at 1,000, and I've found that 900 of those I would have won. And it does the same for the others, and it can then start to gauge how good a position that move would put it in for the rest of the game based on this. But it's doing depth instead of breadth. The problem is this still takes a long time to do. It took weeks and weeks and weeks with like banks of computers to calculate this. So they couldn't do it in real time. So the really cool bit is the bit on the left. So they used 2 neural networks. And what they did is they took a neural network and they used this to train it. So this is now giving us the ability to score positions. So we don't really know whether a position is better or not. But based on the statistics of how likely it is to lead to a win, we can then score it. So they got a neural network, and all it really does is pattern recognition. It recognizes different patterns of play. And so what you can then do is you can say, well, okay, this particular pattern, if I move one piece, it becomes this other pattern. I'll look that up and see what score it got. And so what they did is they spent weeks and weeks and weeks training a model. The initial AlphaGo they gave 100,000 human games to, and then it played itself for like months. And it did something like 140 million games against itself. And they did all this scoring. And what they built was a model. This model you can run on an iPad. So once you've actually trained it, this is all out of band, this you can actually run on an iPad. What was cool about Google AlphaGo Zero is the fact that they didn't actually teach anything about Go other than the rule set. So they improved upon this, and they basically gave it the rules of the game, and they gave it 72 hours, and it got through 3.9 million games, and it won 100% of it. It won 100 matches and lost 0 when it played the original AlphaGo. And it didn't take any, so remember with Deep Blue, you had to understand chess to be able to build all the algorithms and everything. You didn't need to know anything other than the rules. They then taught it to play chess better than Deep Blue in a day, and then they taught it Japanese chess. It's just mind-blowing. But what's really cool about this is Deep Blue, when it lost to Kasparov, it didn't actually learn anything. There was no learning going on. This will learn every time it plays an opponent as well. So that's really, really cool. Let me check what I'm going on. So quickly talk about a couple of different types of AI. So when we hear loads of different definitions of what AI and machine learning are, I quite like these. So artificial intelligence is really just, can we create a computer that behaves a bit like a human? And the sort of stuff we would consider to be kind of common sense and human behavior. And it's usually broken down into 3 types of AI. So there's your weak AI, or artificial narrow intelligence. That's like these game-playing applications. You've then got artificial general intelligence, which is the kind of thing you'd maybe think of as like, if we had a robot, how would that act like a human? That would be the general intelligence. We're not there yet, but we're doing pretty good at A&I. And then ASI is the smarter than human, super intelligent, world-dominating type AI. We're nowhere near that yet. What's interesting about the A&I, 1950, we were talking about building a chess computer. And it could be a human playing chess. It took them a few years to get to that point, but it's kind of fulfilling AI, right? But it wasn't learning anything. We were kind of using some tricks, and it looked like a human. So machine learning is just kind of a subset. AI is kind of like a lofty goal. Wouldn't it be great if computers could act like humans? Machine learning is how we get there. So there's a load of different methods you could use. Machine learning is just the most popular at the moment. So it's a subset of AI. And then underneath machine learning, neural networks. Again, there's lots of different algorithms within machine learning. Neural networks happens to be the most popular of those. And you have a thing called deep learning, which is what these things are doing, which is just neural networks with lots of layers. And that's my AI plus machine learning. That's what a neural network looks like. So you start off creating like a fake neuron. So you have some inputs. You have a calculation that gets done, and you have an output. And what you do is you get a big data set, and you have lots of inputs and expected outputs, and then you pass them both into this, and you just start off with a random value, and you start tweaking how it works. So if you wanted to model something like an AND gate, you put 2 1s in, you'd expect a 1 out. So you feed 2 1s in, and you get 0.3 out. And you tell it, no, that's wrong. So it has another go, and it says 0.5, and you go, warmer, and then it goes 0.989714, and you go, yeah, that's close enough. It's almost 1. And that's how neural networks work. You just start off with this little unit that you retrain with some data. Then you just plug them all together. So perceptron, that's the sort of single unit. If you take the output of that and feed it in as an input to another one, you've built a neural network. And when you start to do lots of these, you get these green ones that are in the middle. So the input is coming out of another one, and the output is going into another one. So we never actually get to see what that's doing. We call that a hidden layer. And if you have lots of those, we call it deep learning. So that's kind of how machine learning works. So why have I talked about chess and Go? What I think is really interesting is, we've had these dreams since sort of the 1950s of being able to do this. And then, in 1997, it was like, oh, look, we've got AI. But was it? I mean, technically it was, but it didn't really learn anything. And then sort of 20 years later, we had the Go engine. And that learned. And you could teach that to not just play Go, but chess, but other games. It was fairly generic. You just gave it the rules and let it play itself, and it could learn how to play better than we could. One of the really cool things about that, it was a very conservative player. So the referee at the time said, it's really interesting because it doesn't play like a human. Humans try to win big, and it would just try and win just enough to get a win, so it wouldn't go for big plays. And it came up with a load of moves people had never seen before, and they now study them in Go schools. So all of the opening moves that AlphaGo uses are now studied in Go schools, because no human has ever used them before, but they're actually really interesting, and there's a whole philosophical debate about whether this is creative or not. What I think is really cool, so I've been at VMware for 2 years, and I had a startup 4 years ago. I used machine learning in that. I just grabbed some Python libraries and built some machine learning, and I was doing medical diagnostics from my bedroom. It was amazing. And I think that's what's happened. So we've had this dream about AI for a long time, and it's never really amounted to much. But now we're at the point that I think the methods are there. You can just get this stuff. You don't need to know anything about chess to train AlphaGo to play chess. It just does. So you don't need to know, real depth about that sort of area. What you did need, though, was a supercomputer to do all the actual training of it. But once you train that model, you could run that on an iPad. So that was pretty cool. Now we live in an age where we don't, you had to be like Google or Facebook to have enough computers to do this. Now we've got the cloud. So if we want to train a model, it takes 72 hours to learn how to play Go? Well, great, okay, so I'll hire 100 VMs in the cloud for 72 hours. It's expensive, but it's not like the billions it would cost me to build a supercomputer. I can rent it for a couple of days, and once it's done, it's done. Then I can ship that model on iPads. Or, that model only has to run for a very short amount of time. It was super efficient. So you can actually use it as a function as a service. So you could spin that up for the fraction of a second it took to choose how to make a play. So if you wanted, you could use the cloud to run that. And so I thought, what's really interesting is we've got, I think the models are now there, and all the theories are there, and we've now kind of got the infrastructure to support it. And you don't have to be one of these big companies to do this. So this is my big bet for what I think we're going to see a lot more of. I don't know, how many people are using containers quite heavily in their organization? Any hands? No one using containers?
Awkward.
Awkward. So, that's kind of what we've seen at the moment. Like, lots of people are starting to adopt that. I think the next thing, once that's happened, this is the next thing that we're going to start seeing people using a lot of. It's got to the point that now app teams can just hire a data scientist. He can build some models. You don't need a supercomputer to build the models. And then they can start shipping them and putting intelligence into their apps, and anyone can do it. And it's this kind of convergence of everything. So this is a shot of cotton spinners in Manchester at the turn of the 19th century. So there's a thing called the Jevons paradox, and basically it's a kind of a flip of supply and demand. So normally with supply and demand, as your sort of supply increases, the demand diminishes. What happened here was coal power was really expensive, and they found that once coal power started to become more economically available to anyone, they thought that, as it became cheaper, they thought, won't be using as much of it once that's a solved problem. And what actually happened was the cheaper it became, the more people started finding uses for it. They use it a lot to describe people driving in cars. So they found that the more economical a car has become, the further people drive. So I think this sort of AI ML thing that we see, and we see the big companies doing, it's now reachable for pretty much anyone to use. And I think there's going to be a sudden massive uptick in the amount of adoption that's going to happen, which I guess is a little counterintuitive.
Cool. Scary stuff. Click.
Thank you.
Okay. When Nick explained that to me, that's what happened. It is mind-blowing stuff. It's very exciting. And what that means to sort of us as operations people and developers is there's a new person at the party. It's Nick over here. He's the data scientist. And actually, they're always in the room. They're always there. They're always doing interesting things. But what they've got now is something that actually works. And it works in a way that we can understand it and we can use it in applications today. Whether that's holding up your iPhone and changing your face to a smiling dog as you use Snapchat or whatever application you like. A lot of the machine learning and the image recognition that we're using day to day on our mobile phones stems from all this deep learning. Joe was talking this morning about Teslas and cars being able to drive themselves. It's all based around this technology and the ability to create these models. So I thought it'd be quite fun to take this model of the data scientist building a model, developer using the model and building an application, and then someone from operations running the application and building and scaling the platform by way of a live demo. So fingers crossed. We'll see how we go. Right, is that branched out to my desktop? Can you guys see that okay? Okay, so I've got a bunch of things here. And assuming the internet connection is still there, we are good. Okay, so what I've got is I'm going to start with the data scientist part. So when I'm building a model, I need to start with lots of data. The more data I can get, the better. But I also need to be able to classify the data and categorize it in a way that makes sense for the model that I'm building. Back to sort of Nick's example of his gate. 1, 1, I'm expecting 1 out. If I get 0.3, I want to be able to say, no, that's not right, try again. And that's the whole point behind the modeling size and the data scientist side of things, is to take that data set, build some classifiers that mean, yes, it's good, no, it's not good, and then the neural nets can be built off the back of that. And that today typically requires some specific hardware. Google have got the TensorFlow processors in our data centers, things like GPU accelerators to accelerate this process, because it's very computationally intensive. Luckily, here's one I built earlier. So if I start up my my machine learning process, and it's based on Python. It's nice and easy to read and start up. But what I'm trying to do is teach a machine to understand things, pictures of things to be precise. So I'm taking a model that someone else has already built, which has been classified and has an awful lot of stuff in it. I'm layering on another layer of intelligence, if you like, so that it can classify slightly better. And in this case, it's going to be some animals and some flowers. So I'm going to kick that off because it still takes a little while to do this kind of thing as it moves through. And what's happening now is somewhere in a nice data center in Palo Alto, there's a TensorFlow processor grinding away, building that model for me. And as a data scientist, I'm hoping that works well. This is my helpful, friendly dashboard explaining to me what I'm building and how the machine's learning. So over time, I'm hoping that those graphs will become a little bit more sensible. But it's very specific knowledge. It's very mathematically complicated. It's confusing enough to look at. And I've been doing this for a couple of months now, and it still makes my head hurt. But that model's being built. While that model's being built, from a development side, I can still focus on building the application. So the app team, I'm going to get a model at some point from Nick that shows me how I can identify a cat and a dog and a plant. So I can continue working on my application. Let's leave that running so I can see what's done. OK, so that's finished. That was quick. Cool. There we go. It's done some cool stuff. I've run this a few times, so the deviation is not that different. But you can see that the more times you run this, the blue lines are how much better it's getting at it.
So you're expecting, you've basically got, this is what I'm expecting, and this is what it's giving me.
Yeah.
And the closer they are, the better.
Yes, right. More accurate. And I can tweak the numbers as a data scientist to try and get it more accurate, i.e. 0.9, 0.99, almost to get it. I'm never going to get it to say, yes, it's absolutely sure that this is a cat or a dog or a whale. But if it's good enough, then it's good enough. And then I can hand that over to the development teams and say, right, here's your model, roll it into the application. So typically a model is now a zipped file that's put on somewhere where I can share it. So this has automatically got pushed out to a storage array. And I can hopefully build something. So if I take my code that I've got here and I rebuild it, and funny enough, this is in containers. That was quick. So I've packaged up my application code. I've taken the new version of the model, and I'm going to push that up to my, my image repository. And this is why developers like containers, right? I've built a new version of the application, and all the thing that changed was the model. So that build process for my application was incredibly quick, because all the other libraries and all the other pieces that make up my application were already in place. They were already in the containers. They were already good to go. So all I did was take the model, put it into my code, and now I've taken that container that is the code, and I'm going to say to an ops guy, hey, cool, new version of the application. Can we run this somewhere? Because I'm expecting millions of users to be able to want to identify cats and dogs, and we spent a lot of money on Nick's tensor processors to be able to do that machine learning part. Now, Mr. Ops guy, how are you going to run that for me? So luckily, I've also got a nice Kubernetes environment stood up that I can do something to run that application. And I'm running that in a way to make it as efficient as possible. So a lot of machine learning workloads are based around, is it a cat, is it a dog? Is that a car, is that a fish? So they're simple questions that we can answer very easily if it's image recognition. Is this hot, is it cold? Is that a 1, is it a 0? So it's simple things. And that leads itself to functions as a service or serverless or whatever you want to call it. Basically being able to ask a question and get an answer back immediately and then moving on with your business logic. So the combination of serverless computing and machine learning is really attractive.
Yeah, I tie that back to the Deep Blue was like the size of a fridge, right? Because it was trying to calculate everything real time. Once you built the model, you can literally play AlphaGo on your iPad if you want to pay for the app.
Yeah, it's really cool. So let's push this out and hopefully get it working. So I'm going to drop onto my Kubernetes cluster in Cloud PKS, and hopefully be able to do something with it. So this is my cluster. As you can see, it's not very big. I'm using 8 gigs of RAM, 2 vCPUs, and I've got the environment running. What I've deployed is I've deployed OpenFAS on top of it to deliver a functions of a service, a serverless framework, and I'm going to redeploy my application. So I've already got it running, so I'm going to just copy that image name. We'll delete the app. Give it a second, and then we'll redeploy it. Okay, deploy a new function. I've got one that I've written myself. And we're going to call it VMUG. Actually, stick with the name because I know it works.
I think there's a few things converging here as well. So if you noticed at VMworld, we announced vMotion support for GPUs, VMs using GPUs, and using GPUs within containers is in beta in Kubernetes at the moment. So I feel like all these things are kind of coming together at the same time. What
we're kind of alluding to here. Okay, so I've got my, my function deployed. So let's test it out. Let's see whether it can actually identify anything. So one of the things that's quite difficult on the internet, apparently, is to find images that are just links to pure images as opposed to lots of adverts these days. So I've grabbed a few that we can test it against. So for the humans in the room, that's a cat, right? Just checking. Let's see if we can get my machine learning model that's been provided by Nick, and my serverless functions do a similar thing. Is it a cat or is it an error message? Fingers crossed. That's both. Excellent. So I've got a warning that I've not written some code very well. But underneath that, I've got I'm pretty certain it's an Egyptian cat, and I am 0.8815673 blah, 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 convinced it's a cat. So
it could be a plastic bag or a keyboard, but that's very unlikely.
It could also be a plastic bag or a keyboard, but we're less confident about those ones. So let's just try one more. I would go and find something on the internet and just bring it up randomly, but that went wrong in my dry run. Let's try this guy, see if that works better. Thinking about it. Okay, so this time we're pretty certain it's a fur coat. That's, well, we're 0.46 certain it's a fur coat.
That's technically right.
So it's technically sort of right, kind of. But I think I'm going to send you that image and say, this is not a fur coat, and you can adjust the model. So let's just do one more, because I like to end on a success. One more. Come on, work it out. What do we think it is? We think it's grey whale, 93.93. Excellent. So that's worked it out. So what's great about this, though, is we've taken that model, but every time I'm running that function saying, is this URL a whale? Is this a cat? Is this a dog? I'm using almost no resources. The only resources I'm burning is the time I'm asking the question, the serverless function is happening. And we've got an iteration count there to see how many times it's been called and how many times it's been executed. But it scales down to 0. So when it's not doing anything, it's literally not doing anything. It's incredibly efficient. Now, if you look at that in conjunction with technologies like Kubernetes and PKS Cloud, where we have smart clusters that scale up and scale back, your ability to run a workload now is based on, actually, I can deploy it, and if it's not doing anything, my worker nodes, my compute nodes aren't going to exist. My serverless functions aren't going to exist to use resources. But when I start to get busy, the serverless functions are going to start to scale up and cope with demand. If that demand starts to impact infrastructure, then the infrastructure is going to start to scale up to be able to cope with that demand as well. My Kubernetes environment is going to grow. But I'm only going to be paying for what's happening at the time it's happening. So I can now iterate quickly on the application. I can use some cool machine learning stuff which stands aside. But when I'm running things in operations, I'm running it in an incredibly efficient manner. And I'm really pleased that all that worked. So we've taken a very complicated thing that took 12, 18 years when we were trying to play checkers, and we've taken it to identifying actual pictures of people in a very short time. And I'm not using much compute power to do it. So it's incredibly powerful. It's very cool. So what does this mean to VMware? Let's get back to the presentation. Should have closed the other ones. There we go. So what does that mean? Well, OK. What's interesting, it's not really about the infrastructure. It's about the applications. It's about taking that model that was very specific, needs GPUs, processor units, and things, to build interesting parts of the application. And sure, you can run that in the data center, but actually running that piece in the cloud where they've already got that investment and they're already iterating on that does make sense. If your business is machine learning, then maybe you do want that in your data center. But having that option to be able to build both, and then combining that with the ability of the functions of a service to take that model, that event model. So Nick's created a new model of the identifier. Now we can identify Santa Claus. The second that file is landed on the storage, that's an event that can trigger a build pipeline. And I can take that, I can roll that into my code, push it to a container, push the container into the repo, and have that running. So technologies like serverless and ML are accelerating the speed that we can deliver applications. So functions as a service, OpenFAS we're using for this, which is written by a guy called Alex Ellis. It's an open source project. He works for VMware, but he spends most of his time sort of iterating on OpenFAS and teaching people about how that works. It's a great way of delivering that capability. So merging the two is something that we're really looking at as VMware, and we've been focusing on quite heavily. But there's projects alongside that. So just delivering functions as a service is great, but in an enterprise, you need to be able to do more to it. So we've got a project called Dispatch that's an open source project, and we're adding more to it. So we're keeping OpenFAS in the middle, or any functions as a service you want, actually. It's pluggable. And we're adding things like API gateways, events, so we can respond to things that are happening on the vSphere platform, identity management to make sure only the correct people can call my functions as a service. So this is what we're doing. We're spending a lot of time looking at the application part as well as the ML part and making it easier to be able to deploy these things in VMware-centric clouds around the world and to make them accessible to people. And alongside that, it would be remiss not to mention the pivotal functions as a service. So sitting alongside PKS and PaaS, Pivotal have launched a service this week. It's in beta, which is a similar function service that sits alongside that stack. And you're going to hear more about that in the next coming weeks and months as we start to roll that out and explain where the benefits of that are. Okay, so where does that bring us? It brings us to the application evolution that Joe was talking about this morning. Applications, traditional applications, VRA, IaaS applications, and up until fairly recently, those data scientists sat in that world. They asked for really big virtual machines, and then they wanted to plug GPUs and things into them. So that was where they sat, and they still sit there to a certain extent. Starting to move towards a hybrid microservice-based applications, where I've got a combination of my fast iterating applications, the data models, talking back to traditional systems. So CAS, containers, and then my cloud-native stuff, my Kubernetes, my PKS, and my platforms as a service, my functions as a service, being able to drive those applications much, much faster. But ultimately, if you think about the application platform what we're building, in order for Nick to be able to build his models, to be able to do that identifying of Santa Claus, he needs lots of pictures of Santa Claus. He needs lots of pictures of dogs, cats, whatever it is he's trying to build. Or an awful lot of recordings of successful Go matches, or the rules. All of that has to sit somewhere. Whether it's public data, whether it's private data, they sit on infrastructure where it needs to be consumed and accessible across the board. And that's what we're doing. We're stitching all this stuff together to be able to deliver these capabilities. So whether we're trying to build on AWS services, hardware in your data center, on VMware clouds, having that consistent platform for me to be able to consume the output from Nick as a developer and be able to push that up into a rapidly scaling Kubernetes platform is what's driving the applications forward and making things faster, quicker, better. And it's a confusing world, right? Only a few of you raised your hands to say you're using containers in anger, and we're standing here talking about machine learning and next generation stuff. They all build on each other. Virtual machines gave us the ability to run containers. Containers gives us an application platform. Application platform gives us serverless functions. And at some point, I'll get a new model from Nick, and I can just roll all that through. So it's a continuum. But so long as we can access everything, so long as everything's pluggable together. And that's the core part, hooking everything together to make it all work. So in closing, I'm still blown away by the stuff that Nick was talking about and explaining to us. The complexity of the machine learning and how incredibly cool it's going to be in the future. Computer vision, understanding voice, being able to talk to Alexa and actually having it understand me as opposed to just repeatedly asking me what the hell I'm talking about. I'm pretty excited about that. But it sits in a particular area of computing. It sits with the data scientists. It's taking that model and what you're going to do with it with the applications and then making it accessible to people either in the business or to end-user customers through our public clouds or however you're going to consume it that makes it interesting. So in my view, we're going to have Kubernetes everywhere. It's the way to run containers at scale. It's a presentation around Kubernetes, so I have to mention service mesh, tying things together on the network. We announced NSX, well, we talked about NSX SM, service mesh, this week at KubeCon. Tying the network with the compute is a key part of delivering this capability. But machine learning, serverless functions, the application-specific stuff is really where it's at. Being able to take something, quickly iterate on it, build something out of the back of that, then take that feedback loop, feed it back around and make it better is what's delivering the business value to people. We talk to financials and organizations that are focused on things like fraud detection and stuff like that. Those feedback loops are key to protecting those businesses and delivering differentiators for those businesses. In the GPUs that are in Teslas around machine learning to drive the cars down the motorways, it's all based on these neural nets, this deep learning, and iterating around on this stuff. But ultimately, the models land up on things like iPads and Snapchat and things like that, where you can change your face to make yourself look like a penguin or a monkey. So that's quite fun as well. But from a VMware perspective, this is what we're looking at with cloud-native applications, delivering the platforms that let you build these things and iterate on them quickly, and to connect the clouds. So connect the TensorFlow workloads that today we're running actually in Google's compute engine onto some storage. That storage was connected back to my PKS instance that was running on the PKS cloud services, and the application that I built and pushed was running on my laptop. So I connected my local machine to 2 different clouds to build that application, and it took less than 2 minutes. So that's incredibly powerful, and I most of the time don't really know what I'm doing, so I'm really pleased that worked. Okay, so with that, that's a sort of whistle-stop tour of machine learning from a scary maths perspective, and then from a sort of implementation perspective. It's really interesting stuff to look at. There's a lot of articles, especially around TensorFlow, about how you can do this stuff. It is possible to run it on your laptop. It's certainly possible to run it in various clouds. It's fun to play with, and then standing that stuff up on a Kubernetes platform and running an application is incredibly satisfying. So with that, any questions, folks? Not that I can see any hands. Oh, question there, yeah. Oh, sorry, question of PFS. What's the question?
Yeah, so as far as I understand it, it's supposed to run on top of Kubernetes. So it's the idea that PFS, I don't know if it's supposed to run on top of EKS, or if PFS contains its own.
Okay, so there was a question about the specific architecture of PFS, but does PFS run on top of Kubernetes, PKS? How's that going to work? At the moment, it sits on top of Kubernetes. So PFS is the core function service is something called Knative from Google. And Knative sits on top of Kubernetes. Exactly how that's going to be packaged, we've not announced yet. So we've announced the capability, we've not announced exactly how we're going to package it up. But yeah, PFS will sit on Kubernetes in some form or fashion, whether it's a standalone Kubernetes or whether it sits on top of PKS or another Kubernetes. Wait till we finish out, come out the beta of that. Any other questions, folks? Wow.
Is anyone looking at, any of your companies looking at or already doing machine learning?
One over there. Excellent. At least one.
Is it interesting?
I'm not doing it, but they're all working a lot with like Talent and Snowflake and products like that.
Okay. I mean, and this is my bet. So my startup, I had a recurrent neural network, which is one of the ones I had up on the list. I was using that to do early diagnostics of diabetes and heart disease in cats and dogs. My other half's a vet. I spent a couple of weeks training these networks, and I was within sort of 95% accuracy of what she was getting. And I was shipping it on mobile handsets, so you could be at home, and rather than wait for your next 6-month checkup, you could do some tests at home, and it would kind of go, yeah, you probably want to ring your vet. That kind of stuff. And at the time, I knew nothing. I spent a couple of weeks with some Python libraries, and I was 95% as accurate as my other half, and she spent, including a degree in her follow-on stuff, about 15 years studying veterinary, specifically things like heart disease. So that was kind of mind-blowing.
How did that conversation go with her?
Yeah, I was like, I can pretty much replace you with this network. She was just like, it's witchcraft. But I think, the fact that I could do that, and I was at home, I was in my bedroom, I used my laptop, I paid for some time in the public cloud to do the actual computation of the models, and then I calculated the other day, if I was running it as functions as a service, I could do 1,000, basically analyzing blood glucose graphs, I could do 1,000 of those for a penny, based on the compute time it took to analyze. It's pretty simple graphs once you get down to it. So yeah, for every 1,000 graphs I was analyzing, it was costing me 1 pence. And I was doing this. So it's got to the point now that, all the techniques are there and you don't need a supercomputer to do it. I really think we're going to be seeing this everywhere. Once people have got their heads around containers, and developers are doing this kind of agile, we're shipping new versions every week, they're going to want to start playing with this stuff. Get a couple of data scientists to build some models, and you're going to start seeing it in all sorts of things.
And ultimately, it comes down to the data. So of those applications you get today, are you willing to share anonymous data with X? When you click the yes button, that's helping build these networks. And both within VMware and pretty much every other organization on the planet. They're hungry for the data, they're hungry for the usage, so you can build these models and make things more interesting and build the next generation of applications with that machine learning, with that intelligence built into it. So next time you're mucking around with applications on your phones or your devices, or trying to teach a car to go around a racetrack using some Lambda functions, Think about that. Think about what you're building, and think about the data that you're feeding up in some cases, because you don't necessarily want to share all your data with absolutely everybody. Cool. I think we're pretty much out of time. Is there any last questions, or are we good? Okay. Thank you very much for your time, folks.
Thank you.